Hello everyone. This video is about graphing logarithmic functions. Um, First of all, we should know what the inverse of exponential functions are. So we learned in the previous section that every function has an inverse. So what's the inverse of an exponential function? For example, we have, let's say, b to the x. F of x equals, let's say, b to the x. And we know that f of x represents y equals b to the x. So we know the steps, we switch x and y. So when you switch x and y, you have x here on the left, y is the exponent. So x equals b to the y. How do I isolate y? We should solve for y, right? So that's the steps. So what is y? With this y. So in the previous lesson, we learned that in order to isolate exponents, we have to use logarithms. So let's just convert this exponential equation to logarithmic equation. So write this as y equals log base, keep the base b, of, go to the other side, x, gives us y. So that's the inverse function. You write the inverse function as f superscript -1 f inverse of x equals log base b of x. So that's the inverse of f of x equals b to the x. So b is the base, x is written beside log. So you don't have to do this conversion all the time. So this is always the same. Base is the base and exponent will be written next to log to find the inverse function. So first of all, we should know that. And second of all, we have two types of exponential equations, as you can remember from the first section. Either the exponential growth, the base is greater than 1, so function is rising from left to right, slowly at first, and then growth is dramatically. Or we have an exponential decay where we have base between 0 and 1. In this case, your function is falling down from left to right, rapidly at first and then slowly. So similarly in logarithms, we have an increased logarithm and a decreasing logarithm function. So our functions will be reflected around the origin. So let's say this is a line y equals x. So there is sort of a mirror image here. So we are just going to reflect this b to the x function around y equals x axis, y equals x line, and we get this red function. Similarly, there is y equals x line here for exponential decay function. We are just going to reflect this function around y equals x line. We get this red function. This is decreasing. This logarithmic function is decreasing. That logarithmic function is increasing. And we're going to learn how to graph them. First of all, we should know that when we find the inverse, we switch the value, the x and y. The rows of x and y's are switched. So the same goes for domain and range. Since we switch the rows of x and y, we have to switch the rows of domain and range because domain represents the x values, range represents the possible y values. So we just have to switch it. For logarithmic functions for both decay or growth, the domain will be the range of the old function. The range will be the old domain of the old function. So what was the domain of exponential functions? It was all real numbers. So you just switch it, your domain becomes range. So range of logarithmic functions are all real numbers, or from negative infinity to positive infinity exclusive. What about range? What was the range for exponential functions? It was 0 to infinity. Now your domain becomes your range. 0 to infinity exclusive, or y is greater than 0. Since you switched x and y, it is x is greater than 0. So we just change the places of domain and range. So graphically, you can also identify it. Remember, for exponential functions, the function is approaching to x-axis, never touching, never crossing it. So when you switch x and y, this time for logarithms, the function is approaching to y-axis, not touching or crossing the y-axis. For both, the same goes for the function is approaching to y-axis, never touching, never crossing. So your domain is from 0 to infinity. 0 is discluded. From 0 to infinity. You have a graph on the right side of origin. You don't have a graph on the left, so you don't have the negative numbers for domain. But for range, it extends in both direction to the infinity, from negative to positive infinity for both of the functions. So there is no limitation for the range. It extends up and down from negative to positive infinity. But there is the restriction for domain. We can't pass through this y-axis, so we just have to have positive values. So positive values for domain, no restriction for range, all real numbers. So those are pretty important. Now let's focus on how to graph them. We did a table of values for exponential functions to graph it. We are going to use the same. We are going to use table of values and point plotting. Connecting the points, we will get our graph. So use the given x values to graph each function. So negative 2 to 2. We already did this in the first section. Substitute negative 2 in the function will give you 1 over 9. Substitute negative 1 for x, it gives you 1 over 3. Plug in 0 for x, it gives you 1. Put 1 for x, 3 to the 1 is 3. Insert 2 for x, 3 squared 9. We can graph this first. At negative 2, I'm at 1 over 9, very close to 0. At negative 1, I'm at 1 over 3, a little bit upper. At 0, I'm at 1. 1 is here. At 1, I'm at 3 up here. At 2, I'm at 9. 2, I'm at 9. So those are the points that I have to connect. By connecting them and extending the graph, I will get to see what exponential function growth function look like. So that's my exponential growth function. So how do I graph logarithmic function? The inverse of this function 3 to the x is f inverse of x equals log base 3 of x. In order to get this graph, we just have to switch x and y values. So this is the idea of finding the inverse function, right? Switching the x and y. So switch the switch the roles of x and y. So we will reverse every ordered pair. 1 over 9 and negative 2. 1 over 3 and negative 1. Your x becomes 1, y becomes 0. X becomes 3, y becomes 1. X becomes 9, y becomes 2. So I use the same ordered pairs, just with different order. I just reversed the ordered pair, each ordered pair. So now start plotting these points. 1 over 9 for x, close to 0. Negative 2 for y, somewhere here. 1 over 3 for x, negative 1 for y, somewhere here. 1 for x, 0 for y, I'm on the x-axis. 3 for x, 1 for y, I'm here. 9 for x and 2 for y, I'm way up here. So connecting points and extending the lines will give us the logarithmic function I am looking for. I want to try this again. One more time. Okay, something like that. My function is approaching to y-axis, never touching, never crossing it, and it's rising from left to right. So that's how exponential growth function, the logarithmic growth function, look like. And the other part of the question is graph its inverse. We did describe the domain and range of the inverse function. We know domain and range of the exponential function. For exponentials, our domain for exponentials, our domain is all real numbers. Range is from 0 to infinity. Since I switched the roles of x and y, I will switch the roles of domain and range too. So my domain becomes range of the exponential function, which is from 0 to infinity. My range becomes domain of the exponential functions, which is all real numbers. So this is how you graph and how you determine exponent, domain and range. You can do the same for decay function by just switching the rows of x and y and point plotting these values on the graph. We will find the graph of exponential, the logarithmic